It's now time in the course to talk about vapor power systems. Vapor power systems are just that. They use a working fluid that changes phase from a liquid to a vapor over the course of a cycle. Traditionally, your home is powered by vapor power plants, or really more importantly, steam powered plants, where we use heat from maybe from coal, burning coal, or nuclear power to heat the working fluid in practical applications, that is water, and that the steam that is created in what is called a boiler is then put through a turbine to produce power, which goes to an electrical generator. That which flows out of the turbine is cooled by cooling water in a condenser and then is pumped back into the boiler. So this most basic cycle I have drawn up here is called a Rankine cycle. The cycles that are used in power plants that are used across the country, across the world, are heavily modified versions of the Rankine cycle. And they can in fact get so complicated that it's not possible to analyze the cycles by hand anymore. But it's instructive for us to at least introduce vapor power systems with the Rankine cycle, and we will look at modifications to the Rankine cycle in further lectures. So here we have state 1, which is typically either a saturated or superheated vapor. This steam or this vapor expands to state 2 at the condenser pressure, producing work across the turbine. We have a condenser. Once all the vapor has been cooled to a liquid state, it is then pumped via the pump back into the boiler. So there are 2 pressure regions in this cycle. We have 4 and 1 that are at the same pressure, and 2 and 3 that are at the same pressure. Okay, so if we draw a control volume around the entire cycle, then our energy balance reduces to just dE CV dt equals Q dot minus W dot. And of course, at steady state, which is where we will analyze these cycles, Q dot cycle is equal to W dot cycle. So Q in minus Q out in the boiler in the condenser is equal to WT minus WP. So let's now look at the efficiency of a Rankine cycle. Of course, remember that thermal efficiency is always W dot cycle over Q dot N. Now, here, let's put a little bit of a augmentation on the subscript of W dot cycle. We'll call that W dot cycle net. So what we want to emphasize here is that W dot cycle is going to be the work that we put into the turbine minus, that we get out of the turbine minus the work that we put into the pump. And that's, of course, over Q dot N. Now, don't get confused with signs here. W dot turbine, of course, will be positive. That's going to be work out. Now, the work that we put into the pump would traditionally have a negative sign here. So you may think, okay, the more work we put into the pump, the greater our efficiency. Well, that's not the case. Make sure that you keep track of your signs such that the greater your pump work, the less efficiency that you will have. So if it helps you feel better to put absolute value bars around W dot P, then please feel free to do so. So in terms of enthalpies, if we draw control volumes around the various components of the turbine and the pump, we will see that W dot P is, of course, M dot H1 minus H2, but all these terms will have an M dot, so let's drop those for now. So this will be H1 minus H2 minus H4 minus H3. I've written it that way because I want this quantity in the parentheses to be positive, and the enthalpy at 4 will be greater than the enthalpy at 3 because I'm doing work on the fluid. And of course, that's over Qn, so we want this to be positive as well, so this will be H1 minus H4. Okay, so that's kind of the working form of the efficiency of my Rankine cycle. Now there's another term called the back work ratio. Ratio that's commonly used in these sorts of problems, and we shorthand this by BWR, and it is essentially the work that we put into our pump, often expressed WP over m dot, over the work that we put into our turbine, W dot T over m dot. And the back work ratio is always a positive ratio. So again, if you want to put absolute values around W dot P, please feel free to do so. So the back work ratio is of course going to equal H4 minus H3 divided by H1 minus H2. Right. So as you can see, what's starting to emerge here is we heavily rely on the enthalpy at each state, 1, 2, 3, and 4, to do analyses of this problem. Let's now talk about a special case of the Rankine cycle, and that is an ideal Rankine cycle. Now, an ideal Rankine cycle will of course have ideal components, so an ideal turbine and an ideal pump. So let's go through the processes of this ideal Rankine cycle, and then we'll draw what the cycle looks like on a TS diagram. So the first, process 1 to 2, is isentropic expansion through the turbine from a saturated vapor at state 1 to some unspecified quality at the condenser pressure. Process 2 to 3, we're going to have heat transfer from the working fluid at a constant pressure through the condenser to a saturated liquid at 3. So we're taking out heat at a constant pressure to get to a saturated liquid at 3, and typically all that heat goes into cooling water, which is circulated through the condenser. Process 3 to 4, we have isentropic compression in the pump to a compressed liquid at state 4, so somewhere left of the vapor dome. And then we're going to heat, process 4 to 1, we're going to heat the working fluid at a constant pressure in the boiler to complete the cycle. Okay, so on a TS diagram, here we are, and here's my vapor dome. So let's start at state 1. All right, so state 1, we have a saturated vapor at some pressure, and of course these pressures up here on top of the pump and before you get to our turbine, those are going to be the higher pressures, and we also expect that 4 and 1 are on the same isobar. So it's probably best if we go ahead and put some isobars on our plot to guide our drawing of the cycle, and I did intend for these to both be horizontal. So let's give that another try. All right, there we go. Okay, so state 1, we're at a saturated liquid. State 2, I'm going to drop isentropically through the turbine. So my temperature is going to drop, my pressure is going to drop, and my enthalpy, or entropy rather, stays the same. Okay. 1 to 2. Now, from 2 to 3, I'm going to cool such that I achieve a saturated liquid. So at a constant pressure during that process. So 3 is going to end up there. Okay. 3 to 4, I'm going to compress isentropically. There we are. So you can see now I'm in the compressed liquid region at 4. And then from 4 to 1, I'm going to follow this isobar back up to 1 to complete the cycle. Okay. So for an ideal cycle, we're going to go 1, 2, 3, 4, and 1. So maybe a real cycle might go from 1 to 2 prime, 3, 4 prime, and then back to 1. So what I mean by that is in real devices. Real devices aren't going to operate isentropically. They're going to have irreversibilities and generate entropy. So we might, from 1, have a process that sees an increase in entropy, gets us out here, then proceeds onwards to 3, and then again have a process that increases entropy in the pump, gets us to 4 prime, and then back to 1. So it's important that we do recognize the differences between an ideal process or an isentropic process and a real process. And here I've denoted the non-isentropic processes as or with dotted lines. All right, so now let's take a little bit of a closer look at our pump. So let's do a control volume about the pump. So in an ideal Rankine cycle, of course, all of my components are internally reversible. So W dot P over M dot, internally reversible, is going to equal integral from 3 to 4 of specific volume dP, or change in pressure. So the question is, why can I write that as the integral from 3 to 4 of dH? All right, so or more, I should pose the question a little differently. If we know this to be true, then why, and we know this to be true, how can these two be the same? All right, so we know this to be true from energy balance, and we know that this is true because of the definition of boundary work, or at least we're relating it back to our definition of boundary work. So let's look at the definition of enthalpy, and of course I'll be taking the differential change of these terms in the in the definition of enthalpy. All right, so delta U in my pump is going to be 0. Why? Let's look at our first TDS equation. Okay, so this pump is pumping a saturated liquid into the compressed region. So my change in volume is going to be 0. It's an incompressible fluid. It's doing it isentropically, so there's no change in entropy. So ds is also 0, which dictates that du must indeed also be 0. All right. Well, since liquids are incompressible, my volume isn't going to change with pressure, so I can pull that outside the integral. And W dot P over M dot is going to be approximately equal to V times P out minus Pn, or the specific volume of my saturated vapor or compressed liquid, or excuse me, yeah, saturated liquid or compressed liquid, and then times the difference in pressure between my inlet and my outlet. So sometimes, you'll see that it's difficult to go to a table and maybe find the entropy or the enthalpy of state 4 because it's a compressed liquid, and oftentimes we're not given that data. So in those scenarios, we can use this equation here to help us find what the pump work is. And do also note that the way that I've written this, this will produce a positive figure. So we're saying, hey, pump work is 10 kilowatts or what have you. Do be aware of your signs as you're plugging these different things back into an energy balance or back work ratio or efficiency, etc. All right, let's now compare the Rankine cycle to a Carnot cycle. So you might recall that Carnot power cycles, not expressed in terms of a piston cylinder assembly, but in terms of vapor power cycles, are very similar to a Rankine cycle, but I think the differences are most apparent on TS diagram. So let's say that each cycle starts at the same spot at 1, and this is, of course, upstream of the turbine. So we have for both cycles a saturated vapor, and for both we're going to expand isentropically through the turbine to state 2. So for a Rankine cycle, we're going to come all the way over to a saturated liquid state at 3. Isentropically compress to 4, and then follow to isobar back to 1. All right, so in the pink here, I've got my Rankine cycle. So how does that differ from a Carnot cycle? Well, 1 to 2 is the same, but do remember that instead of cooling all the way to a saturated liquid at state 3, I'm going to cool down to a point where the enthalpy at, we'll call it 3' for a Carnot cycle, is the same as that which is going into my boiler. So again, the Carnot cycle on a TS diagram is a rectangle, essentially. All right. So what is the implication of this? So both cycles are executing a cycle in which we're getting heat in and we're making power. Well, the implication is that the thermal efficiency of an ideal Rankine cycle is lower than that of a Carnot cycle. Why? Okay, so recall that the Carnot efficiency is the best efficiency that we can attain. And in this Carnot cycle operates between the temperature of Tc and Th. Well, a Rankine cycle operates between Tc and Th minus this bit. So the average temperature of the hot thermal reservoir in a Rankine cycle, because of where 4 falls on this TS diagram, is lower than that of a Carnot cycle. So just recall that eta max, or my Carnot efficiency, is 1 minus Tc over Th. So in real systems, we have irreversibilities that happen, and because of these irreversibilities, we see departures from the ideal Rankine cycle. So let's review quickly what these principal internal irreversibilities are for the turbine and the pump. So for the turbine, the principal irreversibility is the expansion of the working fluid. So recall in a previous lecture that we mentioned that uncontrolled expansion of a substance is a source of irreversibility. I wouldn't call that the expansion of the working fluid in a turbine is uncontrolled, but it certainly is prevalent, and prevalent enough to be irreversible. Unlike a piston cylinder assembly, when we have the expansion of a fluid, that is very much controlled, it's contained, and is typically transferring energy from one form to another, and it's easy to recompress that fluid. But in a turbine, that's just simply not the case, as we have fluid expanding over these blades inside of a turbine. So it's important to note that the work output of an actual turbine is less than an ideal turbine. And it's now a good time to recall the isentropic turbine efficiency, which of course is the work of a real turbine over the work of an ideal turbine or an isentropic turbine. And this will be H1 minus H2 over H1 minus H2S, where H2S denotes the isentropic state, or the enthalpy that the fluid would have if it expanded through the turbine isentropically. All right, so now for the pump. The principal irreversibility in the pump is fluid friction and shear. The work input to an actual pump is greater than an ideal pump. And recall that the isentropic efficiency of a pump is given by the work input to an ideal pump over the work input to an actual pump. So this is expressed as H4S minus H3 if we're using again our Rankine cycle numbering scheme that we had up here earlier, over H4 minus H3.